Question 1.1. Decomposing into partial fractions. We have an already factorized denominator consisting of the product of two binomials, so this just simply breaks down into two fractions, one with each of the binomials. And it's just a number straight above. So now we're going to equate the numerator of the left with the numerator of the right while finding a common denominator. Now we need to find the values of a and b, so what I'm going to do is substitute appropriate values of x in order to eliminate the b and then the a, and to solve for the other one. So I'm going to start by substituting x equals 2, because then that means that is 0, the b is gone, and I'll have just numbers and the a. And that solves to a equals 3. Then I'm going to substitute x equals -1. And that's going to eliminate the a. And we end up with b equal to 2. And substituting back into the first line, there are our partial fractions. This partial fractions question starts with a problem that the numerator and the denominator are of the same degree. We cannot decompose into partial fractions until we have a numerator of at least 1 degree lower than the denominator. So the first thing we have to do is a long division, where we're going to divide x squared minus 4 into x squared minus 3 in order to break this down further. So there we are. We say x squared into x squared goes 1. 1 times x squared minus 4 gives you x squared minus 4. Subtracting, which means changing the sign of the -4, we get a 1. And so the answer is 1, remainder 1. And what that means is we have a 1 from the completed division there, and then that 1 still needs to be divided by x squared minus 4, so it's 1 plus 1 over x squared minus 4, which are then factorized. Now this is going to work as the same as question 1.1, but let's just work on this part of the fraction at the moment. So there we are. Equate the numerators with a common denominator and do your substitutions to eliminate b and then a. So x equals 2 eliminates b, and we get a equal to 1/4. Substitute x equals -2, and that eliminates a, and we get b equal to -1/4. Substituting back into the original, not forgetting that we have the 1 plus, and we're going to end up with 1 plus and then the a, so there, and instead of putting a 1/4 over x minus 2, I'm going straight saying 1 over 4 into x minus 2. That minus and 1 over 4 into x plus 2. When we have a square, remember that, or a cube or whatever, if we have a higher power of binomial, we have to have every power of that binomial below that. So in fact, if we have 2x plus 1 all squared, we have 2x plus 1 all squared as one of the denominators and 2x plus 1 as the other. Equating numerators with a common denominator. Now we can eliminate b easily by substituting x equals -1/2. So we get a equal to 4. Now in order to find the value of b, I'm going to substitute a value in, substituting back in the 4 for A, and I'm going to substitute a value in, and the most convenient is 0 for X. There it is there. So I've substituted 0 into there. That 4 is A now, and we can solve it for B equal to 3. Substitute these values of A and B into the original first line, and there are partial fractions. (2.1) Find the values of A and B where A and B are real that satisfy the equation A plus 3i over 2 minus 5i times bi equals minus 11 minus 13i. Now this we could make quite complicated by trying to get rid of the I on the bottom line by multiplying top and bottom by 2 plus 5i, but why don't we just solve this as a normal equation? In other words, multiply through by 2 minus 5i. There we are, 2 minus 5i multiplying the other side, and I've said bi times a plus 3i. Multiplying that out as a binomial, and of course r squared is negative 1, so we end up with minus 65, and minus 65 minus 22 is minus 87, and 55 minus 26 is 29, and we have the squared on that side as well, becoming minus 1, and so we got ABI minus 3B equals minus 87 plus 29i. Now we have to find the values of A and B. Well, B here, minus 3B is equal to 87. So therefore, and of course, AB equals 29. This is the one independent of the I, so therefore I equate minus 3B to minus 87. This is the one that has the I, therefore I equate AB to 29. This gives you B equal 29, and then we substitute 29 for B in that one, and we end up with A equals 1. So if the square root of x plus ry equals a plus rb, show that x equals a squared minus b squared and y equals 2ab. Now if we have this sort, what I would do is not try to see how I can prove that x equals a squared minus b squared or y equals 2ab. I would get rid of the square root sign first and see what happens. The way to do that is to square both sides. So therefore, squaring the left side, the square root sign's gone, and squaring the right, there it is. Squaring out the binomial, that I squared becomes minus 1. So therefore, we have a squared minus b squared plus 2abi. And here we can now equate. X is the term without the I. There it is there. It's the real part of the complex number. And y is the other part of the complex number. So it's that part there. And there we have x equals a squared minus b squared and y equals 2ab. So now we have to find x and y. If x plus square root of x plus ry equals 5r minus 12. To solve from here, all we have to do is substitute into here, a and b. There we are. X equals, if we have a plus rb, well, this is 5r minus 12, so therefore minus 12 is a and 5 is b. So I'm going to substitute minus 12 for a, 5 for b. X is equal to a squared minus b squared, so I substitute those numbers in for x. And y is 2ab, so I substitute those numbers in for y. 2ab. So we're given this fourth degree expression, and we're told that 1 minus 2i is a 0 of g of x. Use this information to show that x squared minus 2x plus 5 is a factor of g of x. Well, there are no unreal numbers there, no complex numbers within there, and if x equals 1 minus 2i is a 0, then that means that 1 plus 2i must be a 0 as well. So there are factors, x minus the first 0 and x minus the second 0. So there they are there, those two factors. I'm going to multiply them together in order to give a second degree or quadratic factor. Take out the inside brackets and rearrange them so we give ourselves a difference of squares. There's the difference of squares. Squaring out x minus 1 all squared, and there is minus 4 times minus 1, which gives me that. And there we are to see that x squared minus 2x plus 5 is a factor of g of x. Now, in order to find the other zeros, we need to factorize this further. We already know that x squared minus 2x plus 5 is a factor from 2.3.1, x squared minus 2x plus 5. So now that means that the first term must be x squared in the second factor to give us x to the 4. That's a 25, that's a 5, therefore the last term in the second factor must be 5. 5 5s are 25. We don't know what the middle term is, so we'll call it k, plus kx. Now we're going to just equate the coefficients, well, the terms containing x. Now that beats x squared out. That minus 2x times the 5 will give us an x term, and that 5 times the kx will give us an x term, and there is the x term. So this is now factorizing by inspection. I could do the squareds instead. So I could say x squared times 5 is, I'm doing the cubes. I could do the squareds or the cubes, sorry. Alright, so here I could say x squared times kx. So there's kx cubed, and minus x cubed times 5. Right. Let's say that again, I'm talking nonsense. X squared times kx gives me my kx cubed. Minus 2x times x squared gives me minus 2x cubed. So I've got the two x cubed terms, and they must equal the x cubed term. We could drop the x or drop the x cubed. Just by dividing through by them. And that gives the value of k in either case. So therefore I can now take that minus 4 and substitute in instead of k. So there it is. And now the other roots are either factorized, and if they won't factorize, we use quadratic formula. There it is there. And I'm going to simplify. I could take out a 4, which becomes 2 on the outside, square root of 4. So we end up with 4 plus 2 times the square root of minus 1, so 2i, all over 2, and divide into both. So there are the other roots, 2 plus or minus I. On to absolute value, 3.1.1. Absolute value of 2x plus 1 minus x minus 3 equals 0. Now, I'm going to take the non-part of the absolute value to the other side. And remember, the easiest way to solve one of these straightforward absolute value sums, really what it means is absolute value means it's either the positive of 2x plus 1 or the negative of 2x plus 1. Whether you put the positive or negative part of a number into the absolute value, you'll end up with the same result. But we'll just go straight and say, well, 2x plus 1 equals plus or minus the right-hand side. Solving, if we have the plus, we have x plus 3. If we have the minus, we have minus x minus 3. And that gives us x equals 2 or minus 4 over 3. Remember, of course, that with absolute value equations like this, we need to check the answers. So I substitute both in, and they do work. So both answers are checked and fine. This is going to work in the same way. So there's the quadratic expression equals plus or minus 6. That gives us two quadratic equations. So there we factorized and we factorized, no quadratic formula needed. So there are four answers. Once again, you need to check by substitution, and the answers are checked and fine. Now this one's a slightly different case. Remember that if all else fails with the absolute value, you can always go back to definition, which is exactly what I'm going to do here. So first of all, let's take the 6 to that side. So we get x absolute value of x squared plus 7 absolute value of x equals 0. We could, of course, cheat and just say, well, that means, well, the absolute value of x squared is x squared. There's a shortcut. I've done it the long way around. You could do it the shorter way around. But now, remember, here's the definition. If the absolute value of x equals x if x is greater than 0, negative x if x is less than 0. So in this case, if x is greater than or equal to 0, we can just drop the absolute value sign there and there. If it's less than 0, then that is still absolute value of x squared, or negative x all squared, which is x squared. So, and that becomes minus 7x. So now solving those, factorize the top, factorize the bottom, and that follows that x is equal to 0. X cannot equal to negative 7 because this is only if x is greater than or equal to 0. This one follows that x equals 0, which we already have, and x would equal 7, but x cannot equal 7 because x is less than 0. So there's our answer. You don't need to check this one because you've done it from definition. Sketch this graph. Now remember that the absolute value graphs are a V shape and they have a vertex point. It's like the turning point of a parabola, where the lowest X absolute value could go is 0, and that happens when x equals 2. And when x is equal to 2, if you substitute in, y is equal to minus 3. So the vertex point, the tip of the V, is 2 minus 3. The y-intercept, well, just put 0 for x, and you get negative 1. X-intercepts, we're going to equate that to 0. So we end up with x minus 2 equals plus or minus 3. So x is minus 1 or 5. And there's the graph. You could also do it by plotting if you want. You could say, well, this is going to turn, it's going to change at x equals 2. So you substitute 2 into it, you get minus 3. So we know that point is there. And you can substitute one value below x equal to 2 and one value above x equal to 2. And it'll give you a V shape as well. This one here, because we have an x on the outside as well, I'm going to revert to the definition of absolute value again. Good old definition. So there we are. And it's going to be if x plus 1 is greater than or equal to 0, if x plus 1 is less than 0. So there we are. If x plus 1 is greater than or equal to 0, those absolute values just become brackets. X plus 1 less than 0, we have to change the sign at the x plus 1. And that gives me two graphs. Y equals 2x minus 2 if x is greater than or equal to minus 1. And y equals minus 4 if x is less than minus 1. So there are the intercepts of y equals 2x minus 2. So there's the graph y equals 2x minus 2 with the intercepts of minus 2 for y and 1 for x. Notice it stops at x equals minus 1 because this is only for x greater than or equal to minus 1. I have shown a light continuation of that graph, and I've shown a light continuation of this one, where y equals negative 4 is a horizontal line going through negative 4, but it's only for x less than negative 1. Question 3.3, we have a parabola and a straight line intersecting at those points. So it's given to you that it intersects at those points. I'm very sorry, I don't know where 2.5 comes from. It should be 3.6, so that's an error in the actual question, but it does show it on the graph anyway. But you don't need that information, because use the information given on the sketch to draw on the answer sheet provided graphs of h of x equals the absolute value of x plus 3 and j of x equals the absolute value of x squared plus x minus 6. Now, the absolute value of x plus 3 means that x plus 3 cannot be below 0. So in fact, what happens is that this part of the graph here is not allowed. It's going to change signs. It's going to flip up that way. That's what's going to happen. For the parabola, it cannot be less than 0, so that part of the graph is not permitted. It's going to change the opposite side. So in effect, we're going to end up with the graph going this way instead. So there's our graph. And you just do it by that knowledge. You don't need anything else. Notice minus 6 1/4, 6 1/4. Still minus a half. Still the same x-intercepts. And this is a reflection of G. H is a reflection of G there. Now, all right, so these two graphs intersect at the same point as g of x and f of x, as well as the third point there. And you have to calculate the coordinates of this third point. So consider what the equations of these lines are. That's the normal equation. That's the normal equation there. This one is not. If we go back there we are. That's the equation y equals x plus 3 there. But this is now the negative of x squared plus x minus x. So we're actually finding the point of section of a graph which is y equals minus of x squared plus x minus x and y equals x plus 3. So therefore the minus of x squared plus x minus x and y equals x plus 3. And we're going to solve the quadratic. There we are, factorizing. We're going to eliminate the minus 3 because this is clearly the positive point we want. The minus 3 is there anyway, where they do intersect. So therefore x equals 1. Substituting the 1 into the equation, we end up with y equals 4. And so therefore the point is the point 1, 4. Notice I don't have to give the point because it says calculate the coordinates of this point. So if I just put x equals 1 and y equals 4, then that's fine as a final answer.